Hello, I'm Jackson Kauk, and this is an overview of atomic clocks. So why do atomic clocks matter? So atomic clocks are very important because they have very small timing errors over time. Atomic clocks are also used in GPS and satellites. Accurate time gives us accurate technology. This is very important because GPS works by calculating how long it takes for signals to travel, and if the timing is wrong, then your location becomes wrong. So that's why this is so important in GPS, but I'll get into this a little bit more. This is just a little preview. So what is an atomic clock? So if we think about it in like an easier standpoint, something that we can actually think about, something that's not quantum, we'll look at a grandfather clock. So grandfather clocks regulate time using a pendulum that acts as a harmonic oscillator. Releasing a gear train at consistent intervals, atomic clocks kind of just work in the same way, but instead of using this pendulum, they use the natural resonance frequency because atoms naturally vibrate at extremely consistent frequencies. So how do atomic clocks work? Atoms have quantized energy levels, and electrons in atoms can only exist in specific energy states. Cesium atoms are commonly used because their transition frequency is very stable. And atoms also naturally oscillate, like I also said previously. And when atoms transition between the energy levels, they oscillate at this fixed frequency. So to the right, I know this is just a very basic diagram, but we just have these different energy levels, and when the atoms transition between them, they oscillate at like this fixed frequency, and that's something that we can measure. So just adding on to what I just said. So then microwave signals are applied, and when the microwave frequency exactly matches the atomic frequency, then the maximum energy absorption occurs, and this is just called resonance. So the microwave signal is just a signal that is sent through the atoms, and the microwave frequency is adjusted until it matches the resonance frequency, and then we get resonance. And resonance is just when the external frequency matches our natural frequency. And normally in an atomic clock, scientists adjust the microwave signal until the resonance is reached. And once the system detects this maximum absorption, it knows the signal is perfectly matched to the atom's natural oscillation frequency. So the clock then locks onto this frequency and uses it as extremely precise reference for measuring time to keep the clock accurate. And then we also have a feedback loop. A feedback loop constantly checks whether the system stays at resonance, and it just corrects any error. If the microwave frequency drifts even slightly because of environmental effects like noise, the system automatically corrects itself and retunes the signal back to its like correct frequency. So how I kind of look at it is it's just this little like voltage shock, I guess you could say. And if it's off at all, then the feedback loop comes in and plays a major role. And the feedback loop is very important. And then the oscillations are counted. And a little fun fact, like after all of those oscillations, 1 second has passed, and we know this from the cesium-133 atom. So the feedback loop is very important. So here's a diagram, and I'll just kind of go through it. So after the atoms pass through the detector just checks how many atoms reach the excited state. And if too little atoms are excited, then the system knows that the microwave signal's like it's slightly off. And like what is it off by? It's off by the atom's natural frequency. So that's something that you just kind of got to wrap your head around. Like the atom has a natural frequency, and we're just like, we want to match that. And then, so if it's slightly off, it'll go into the feedback loop, and then it adjusts the quartz crystal oscillator until maximum resonance is reached once again. So what are these used for? What are the real world applications? You're probably asking yourself that. Like, what's the importance? GPS systems. One of the most important real world application of the atomic clocks is GPS technology. I don't know about you guys, but I like just plugging in the GPS and going. So thank God for atomic clocks. GPS satellites each contain atomic clocks that send very precise timestamps to Earth and your phone or GPS receiver. This just calculates the position by measuring how long it takes for signals from multiple satellites to travel to you. And the satellites just use the atomic clocks to send the very precise timestamps, like I was talking about. These signals travel at the speed of light, so even the smallest timing error can create very big location errors. A 1 second error would place you nearly 1 billion feet away from your true location. So that's why these have to be like truly precise. Another main application is telecommunication and the internet. Cell phone towers use atomic clocks to stay in sync, and internet servers and data centers also rely on this precise timing. Yeah. And when you make a phone call or send a text, probably something that you guys have all done today, these cell towers have to coordinate, and they all have to coordinate their timing very well together and very accurately. So the signals are routed correctly between towers and devices, which then gets the message. And then on the right here, we have this diagram. And we have 24 satellites that are used for GPS systems. 24 is the minimum that we need. I think we actually have 32. But for GPS, there's 3 that work for you. So where you are at, we only need 3 of them that will work together to get your precise location. And that's why, like I said earlier, if these timing errors were off, we wouldn't be able to tell where you were. So in my research, I found 2 main atomic clocks, and this was cesium and hydrogen. So I'm just going to kind of compare them. And I found that different types of atoms can be used to make atomic clocks, but 2 of the most common that I found were obviously cesium and hydrogen. So just the cesium clocks, something that I found is that they're the international standard for defining the second, which I explained earlier, which is, I think, pretty cool because we're just saying that a second is a second, but how? And cesium clocks are very, very stable. And they're extremely stable over long periods of time, which makes them ideal for national time standards, GPS systems, and also using them for scientific research if it need to be. And they're also very widely used. Now we have the hydrogen clocks, and these are very precise over short time periods. And I'm not talking short as in a couple minutes, a couple days, I'm talking these are still very precise over years. These are more often used in space applications because they're more precise and they're just better. For that, they're just better in their own way. Both clocks rely on the same quantum mechanical principles, but scientists choose between which one they want, whether they need better short-term precision or stronger long-term stability. That's kind of what I'm trying to get across. They both have their own advantages. So what is noise? So noise is just any disturbance that interferes with the clock's frequency measurement. It just makes it harder for the system to stay locked onto the resonant frequency, resulting in this less precise timekeeping. Yep. And then in conclusion, these are my main takeaways. Atomic clocks are one of the most important technologies that have been developed in modern physics. And unlike traditional clocks that rely on mechanical motions, like we saw with the pendulum and the grandfather clock, the atomic clocks use quantum energy transitions in atoms to measure time with extreme precision. Their accuracy comes from the stability of atomic frequencies and the ability to be able to lock onto the resonance using feedback loops. Although noise and motion can affect this stability, feedback loops normally do a pretty good job at helping with that. Atomic clocks are very useful, and they're something that I didn't really know about previously to this. And my research has brought me to the conclusion that atomic clocks are very important. I hope you guys enjoyed. Here are my references. If you guys have any questions, feel free to ask.